Jurassic Park accidentally created the most successful disinformation campaign in scientific history. Every museum display, every toy, every documentary you watched as a kid drilled the same lies into your brain until they became facts. That's why today I'm breaking down every single dinosaur myth that modern paleontology has completely destroyed and showing you exactly why the real animals were so much stranger. Starting with the most dangerous lie Hollywood ever told you, T-Rex vision. The scene is burned into collective memory. Alan Grant freezes, T-Rex looming 2 feet away, and whispers the worst survival advice in cinema history. Don't move. It can't see us if we don't move. Millions of people walked out of theaters in 1993 believing Tyrannosaurus had motion-based vision like a frog. Here's the thing, that's not just wrong. It's the exact opposite of reality, and the scientists have been screaming about it for 20 years. Ken Stevens spent over a decade at the University of Oregon building the Dinomorph project, mapping visual fields across 7 different theropod species using computational models of skull structure. His 2006 study published in the Journal of Vertebrate Paleontology concluded that T-Rex had a binocular overlap of 55 degrees. For context, hawks have 40 to 50 degrees. Stevens estimated visual acuity up to 13 times sharper than human vision, with a limiting far point around 6 kilometers. Our limiting far point is 1.6 kilometers. Its eyeballs were the size of softballs. The skull tells you everything. T-Rex evolved an extremely wide rear skull with a narrow snout, pushing the eyes forward into the perfect predatory configuration. CT scans of multiple specimens including Sue, the most complete T-Rex ever found, show massively developed optic lobes in the brain and evidence of rapid eye-head coordination. Lawrence Whitmer and Ryan Ridgely at Ohio University confirmed T-Rex also had the most acute sense of smell of any non-avian dinosaur they studied. As Stevens put it directly, if you're sweating 1 inch from a T-Rex nostril, it would figure out you were there anyway. But here's where it gets annoying. Michael Crichton's original novel actually explained the vision limitation as a side effect of using frog DNA to fill gaps in the genome. That was explicit science fiction. Spielberg dropped that explanation from the film entirely, leaving audiences to assume it was real paleontology, and it worked. 20 years of research can't compete with one dramatic movie scene. If you think that's the only thing Jurassic Park got catastrophically wrong, wait until you hear what those arms could actually do. T-Rex arms are the internet's favorite punchline. Tiny, useless, couldn't reach its mouth, couldn't scratch an itch. Every meme and joke for the past decade treats them like evolutionary mistakes. Before you make another short arms joke, you should probably know they could bench press you. Twice. Here's what nobody mentions. Those arms were roughly 1 meter long, 3 feet. Short compared to a 12-meter body? Absolutely. But in absolute terms, they were the size of an adult human arm. When Henry Fairfield Osborn first described T-Rex in 1905, he was so confused by the proportions that for the famous 1915 American Museum of Natural History mount, he literally substituted longer 3-fingered arms from a completely different dinosaur. The actual complete T-Rex forelimb wasn't found until 1989. Kenneth Carpenter and Matt Smith published the first serious biomechanical analysis in 2001, and the findings were shocking. T-Rex arms were stoutly built and well muscled with extremely thick cortical bone. The bicep alone could curl 199 kilograms. That's 439 pounds. For comparison, that's 3.5 times more powerful than a trained human bicep. The range of motion was limited, only about 40 degrees at the shoulder and 45 at the elbow, but the structure was optimized for a specific function, gripping struggling prey while the jaws did the killing. And we know they use them hard. Paleontologists have found stress fractures on T-Rex wishbones with prominent healing calluses, proving the arms endured serious strain during life. Kevin Padian at UC Berkeley proposed in 2022 that the arms may have actually shrunk over evolutionary time to prevent accidental amputation during group feeding. When multiple T-Rex converged on a carcass, shorter arms meant less chance of losing a limb to a neighbor's bite. Komodo dragons lose limbs this way constantly. But here's the really interesting theory. Reducing arm mass shifted the center of gravity closer to the massive hind limb. Computer models suggest this may have improved agility and turning speed. In other words, T-Rex traded arm length for better handling. That's not a design flaw, that's optimization. At least those arms existed, unlike the predatory behavior that supposedly never happened. The scavenger theory. Jack Horner became the most famous paleontologist in America by arguing that T-Rex was basically a giant vulture, too slow to hunt, arms too short to grapple, grapple, vision too poor to track prey. He pitched it as the ultimate predator that wasn't actually a predator at all, just an opportunistic scavenger stumbling around the Cretaceous eating whatever it found already dead. His 1994 lecture, quote, Zero, made him a media sensation and the go-to scientific consultant for Jurassic Park. There's only one problem: he never published it. Horner later admitted in a 2011 paper that the scavenger hypothesis was never submitted to peer-reviewed literature. He used it as a teaching tool to get students thinking critically about assumptions, but by then, the damage was done. Millions of people believed the debate was real, that scientists were genuinely divided on whether T-Rex could hunt. The actual scientific community was never divided. They had the evidence. In 2013, Robert De Palma and David Burnham published the smoking gun in the Proceedings of the National Academy of Sciences, a T-Rex tooth crown embedded between two hadrosaur tail vertebrae. And here's the kicker: the bone had grown around the tooth with clear signs of infection. The prey animal survived the attack and lived for years afterward with a T-Rex tooth lodged in its spine. You cannot scavenge a living animal. Then there's the coprolite. Karen Chin described it in Nature in 1998. King-sized, 44 centimeters long, containing 30 to 50% crushed bone fragments from juvenile dinosaurs. Producing that requires enormous bite force applied to fresh bone. Scavengers don't pulverize skeletons. The speed argument collapses under scrutiny too. Yes, biomechanical studies by John Hutchinson and others estimate adult T-Rex topped out around 16 to 40 kilometers per hour. Not exactly blazing, but its primary prey, hadrosaurs and ceratopsians, were constrained by the same physics. A moderately fast predator chasing moderately fast prey is still predation. Thomas Holtz Jr. summarized the current consensus perfectly. T-Rex was an active predator and an opportunistic scavenger. Exactly like every large modern carnivore from lions to grizzly bears, the controversy was always a media phenomenon, not a scientific debate. But if you think Hollywood got T-Rex wrong, wait until you see what they did to velociraptors. Velociraptor size. The raptors in Jurassic Park were 6 feet tall and 200 pounds, intelligent pack hunters that opened doors, coordinated ambushes, and murdered everyone they encountered. Terrifying, iconic, completely fictional. Real Velociraptor mongoliensis was the size of a large turkey, roughly half a meter tall at the hip, 1.5 to 2 meters long nose to tail, and 15 to 20 kilograms. Its skull measured 23 centimeters. You could punt one across a room. The mix-up has a specific origin story. In 1988, paleontologist Gregory Paul published Predatory Dinosaurs of the World and controversially reclassified the larger Deinonychus antiropus as a species of velociraptor. Michael Crichton was writing Jurassic Park at the time, adopted Paul's taxonomy, and later told John Ostrom directly that he chose the name Velociraptor because it sounded more dramatic. Then Spielberg made them even bigger because he was unimpressed by Deinonychus' size. The dinosaurs on screen aren't velociraptors. They're not even accurate Deinonychus. They're movie monsters. Ironically, Utahraptor, a genuinely human-sized dromaeosaur, was formerly named in 1993, the exact same year Jurassic Park released, but it hadn't been described during production. The filmmakers accidentally predicted a discovery, but here's where it gets worse: the skin is completely wrong. In 2007, Alan Turner, Peter Makovicki, and Mark Norell published a study in Science documenting the discovery of 6 evenly spaced quill knobs on a Velociraptor ulna. Quill knobs are definitive proof of large wing feathers attached to the forearm. As Norell stated, if animals like Velociraptor were alive today, our first impression would be that they were just very unusual looking birds, not scaly reptilian killing machines, feathered, possibly colorful, likely making weird chirping sounds. And the pack hunting behavior? That's contested too. A 2020 stable isotope study by Joseph Fredrickson analyzed Deinonychus teeth and found that juveniles and adults had different isotope signatures, meaning they ate different prey. True cooperative pack hunters like wolves share prey across age groups. The evidence suggests dromaeosaurs hunted solo, or in loose competitive aggregations, more like Komodo dragons mobbing a carcass than wolves executing coordinated takedowns. So every single thing Jurassic Park showed you about velociraptors was wrong. The size, the skin, the behavior, even the name. But at least they got the color accurate, right? actually about that. Dinosaur colors. For 150 years, every dinosaur painting showed the same palette. Gray, brown, muted greens, scaly skin modeled on crocodiles and monitor lizards because that's what paleontologists assumed extinct reptiles must have looked like. The word dinosaur itself, terrible lizard, coined by Richard Owen in 1842, locked in this framing from day one. Artists from Charles R. Knight to Rudolf Zallinger reinforced it through iconic murals that defined public imagination for generations. Museums displayed them as dull, plodding monsters. And nobody could prove otherwise because color doesn't fossilize, except it does. The revolution started in 1996 with Sinosauropteryx discovered in China's Liaoning province, the first non-avian dinosaur found with feather-like structures preserved, but the real breakthrough came from a Yale graduate student named Jacob Winther, who in 2008 realized something everyone else had missed. Those tiny structures and fossil feathers that scientists had been dismissing as bacteria for decades weren't bacteria at all. They were melanosomes, pigment-bearing organelles whose shapes directly correlate with specific colors. By 2010, 2 landmark studies changed everything. Zhang and colleagues published in Nature showing that Sinosauropteryx had a ginger and white striped tail with counter shading and a dark bandit mask across its face. Then Li, Winther, and their team published the first complete color map of any dinosaur in science. The chicken-sized Anchiornis huxleyi had a gray body, black and white spangled wings, and a reddish-brown mohawk crest. Yale ornithologist Richard Prum described it as a punk rock magpie. In 2012, Microraptor was shown to have iridescent black plumage like a starling, making it the earliest known example of structural color in a non-avian dinosaur. Even armored dinosaurs had color. The remarkably preserved Borealopelta from 2017, a 3,000-pound ankylosaur, covered in spikes and armor plates, displayed reddish-brown pigmentation with counter shading. That detail is crucial. Counter shading is camouflage used by prey animals trying to hide from predators. This tank-sized armored herbivore needed to hide, implying predators fearsome enough to threaten something that weighed as much as a car. Over 40 species of feathered non-avian dinosaurs are now confirmed. The discovery of feather-like filaments on the ornithischian Culindrodromeus in 2014 suggests feathers may trace back to the common ancestor of all dinosaurs. The dull gray monsters in old museum paintings never existed. Real dinosaurs came in colors we're only beginning to document: vibrant, patterned, iridescent. But if scientists got the colors catastrophically wrong for a century and a half, what else did they misunderstand about basic dinosaur anatomy? Tail dragging. Every museum mount, every textbook illustration, every plastic toy from the early to mid-20th century showed dinosaurs dragging limp tails behind them like oversized lizards. Theropods like T-Rex stood nearly upright in what paleontologists called the kangaroo posture, spine tilted at 50 to 60 degrees, tail scraping the ground. This image dominated public consciousness for nearly a century. It originated with Louis Dallo's 1880s reconstruction of Iguanodon, which he literally modeled on an actual kangaroo skeleton, and was cemented forever by Henry Fairfield Osborn's iconic 1915 American Museum of Natural History T-Rex mount. That mount stood in the wrong pose for 77 years. Here's the thing, the fossil evidence always contradicted this. Out of thousands of dinosaur trackway sites documented worldwide, tail drag marks are conspicuously rare. Kim and Lockley's comprehensive review found only 24 definitive examples associated with dinosaurian tracks. Even the massive sauropod trackways discovered by Roland T. Byrd in Texas in the 1930s showed no tail impressions whatsoever. These were animals weighing 30 to 40 tons, leaving deep footprints in mud, and somehow their tails never touched the ground. The physics make it obvious in retrospect. The tail functioned as a critical counterbalance to the head and torso. Dinosaur vertebrae had interlocking projections called zygapophyses that created a stiff horizontal beam. Biomechanical modeling confirmed that the upright tail-dragging posture would have dislocated the hip joints. The animals physically couldn't stand that way for extended periods without catastrophic skeletal failure. John Ostrom's 1969 description of Deinonychus was the turning point. He compared its tail vertebrae to those of flightless birds and concluded the backbone was held horizontal, not vertical. His student Robert Backer evangelized this revelation in a 1975 Scientific American article that coined the term dinosaur renaissance. The American Museum of Natural History finally dismantled its incorrect T-Rex mount in 1992 and unveiled the corrected horizontal posture in 1994. But here's the depressing part. A study by Ross, Dugan, Haas, and Allman asked college students to draw T-Rex from memory. The average spinal angle in their drawings was 50 to 60 degrees, nearly identical to Osborne's 1905 reconstruction. The correction happened 30 years ago in museums and 55 years ago in scientific literature, yet cultural artifacts and childhood memories perpetuate the myth more effectively than corrected science reaches the public. If it took paleontology a century to figure out that tails don't drag, maybe we should double check what else they classified incorrectly. Pterodactyls. This might be the most forgivable myth on the list because pterosaurs, plesiosaurs, and mosasaurs lived alongside dinosaurs, were all large reptiles and appear together in literally every dinosaur movie and toy set ever made. The Jurassic World franchise features Pteranodon and a gigantic mosasaurus without bothering to distinguish them from actual dinosaurs. Kids grow up grouping them all together, museums display them in the same halls, and taxonomically speaking, calling a pterosaur a dinosaur is an error of the same magnitude as calling a human a marsupial. Dinosauria is defined by specific anatomical features. The most critical is a perforate acetabulum, a hip socket with an open hole that allows an erect legs under body posture. This is what separates dinosaurs from other reptiles that sprawl. Pterosaurs are archosaurs, the broader group that includes dinosaurs, crocodilians, and birds, but they branched off separately. A 2020 study identified lager-padded archosaurs as pterosaurs' closest relatives, confirming they sit on a completely distinct evolutionary branch. Pterosaurs evolved flight independently from birds and bats through a membrane stretched between an enormously elongated fourth finger and the body. Dinosaurs never did this. Plesiosaurs aren't even close. They belong to Sauropterygia, an entirely separate reptile lineage that returned to the ocean. Long necks, paddle flippers, not dinosaurs. Mosasaurs are even stranger. They're squamates, giant marine lizards more closely related to modern monitor lizards and snakes than to any dinosaur. They had forked tongues and shed scales like their living cousins. The first mosasaur was discovered in 1764, decades before major dinosaur finds, yet people still call them sea dinosaurs. Here's the beautiful irony. The only flying reptiles that are dinosaurs are birds, descendants of theropod dinosaurs that evolved powered flight roughly 150 million years ago. Meanwhile, pterosaurs, the ancient reptiles that actually flew during the Mesozoic and dominated the skies for 150 million years, are not dinosaurs at all. They went extinct 66 million years ago in the same event that killed non-avian dinosaurs, but they were never part of the dinosaur family tree. The confusion is understandable. They lived in the same ecosystems, died in the same extinction event, and Hollywood lumps them together because audiences don't care about cladistics. But scientifically, it's like putting whales in the fish section. Superficially reasonable, fundamentally wrong. And speaking of things that shouldn't exist but somehow do, let's talk about the dinosaur that was erased from science for over a century, Brontosaurus. For generations, the actually correction went like this: Brontosaurus isn't real, it's actually Apatosaurus. Correcting someone who said Brontosaurus was a way to flex paleontology knowledge, museums changed their labels, textbooks struck the name, and everyone who grew up loving Brontosaurus had to accept that their favorite dinosaur never existed. Except it did, and as of 2015, it exists again. This saga is 138 years of scientific drama that reveals exactly how messy taxonomy can get. The story begins during the Bone Wars, the legendary rivalry between O.C. Marsh and Edward Drinker Cope, two paleontologists who hated each other so much they literally dynamited fossil sites to prevent the other from excavating them. Marsh named Apatosaurus in 1877 from a partial skeleton. 2 years later, in 1879, he named Brontosaurus from a more complete specimen found at a different quarry. In 1903, Elmer Riggs at the Field Museum concluded the two were too similar to justify separate genera, and under taxonomic priority rules, Apatosaurus, published first, absorbed Brontosaurus. The name Brontosaurus refused to die culturally. It starred in the first animated dinosaur film, Gertie the Dinosaur, in 1914. It appeared on controversial US postage stamps in 1989. Stephen Jay Gould wrote an entire essay titled "Bully for Brontosaurus," defending the name's cultural importance. Meanwhile, museums were compounding the confusion by mounting Apatosaurus skeletons with the completely wrong skull. They used a boxy Camarasaurus head instead of the correct elongated horse-like one. This error persisted until 1981. Then, in April 2015, everything changed. Emmanuel Chop, Octavio Mateus, and Roger Benson published a 298-page phylogenetic analysis in the journal PeerJ. They examined 477 anatomical features across 81 individual sauropod specimens from 18 museums on multiple continents. Their conclusion was definitive: Brontosaurus excelsus differs from Apatosaurus species in at least a dozen key skeletal characteristics, as many differences as separate long-accepted genera like Diplodocus and Barosaurus. Brontosaurus has a narrower, taller neck and unique shoulder blade features. 3 valid species were recognized. The Yale Peabody Museum held a renaming ceremony within 1 week of publication. Brontosaurus is now considered a valid genus by most paleontologists, though some debate continues over where exactly to draw genus-level boundaries. The resurrection was so significant that the 2015 paper is one of the most downloaded in PeerJ's history. So if you grew up being told Brontosaurus was fake, you were right at the time. If someone corrects you today for using the name, they're actually wrong. Science doesn't just move forward, sometimes it circles back and admits it overcorrected, but at least paleontologists never claimed dinosaurs had 2 brains. Oh wait, Stegosaurus brains. The 2-brain Stegosaurus is one of paleontology's greatest tall tales, and it started with legitimate confusion. O.C. Marsh was examining Stegosaurus specimens in the 1880s and discovered something bizarre. The sacral cavity, the passage where the spinal cord runs through the hip vertebrae, was 20 times larger than the brain cavity in the skull. 20 times. In 1881, he described this enlarged space as a posterior brain case, speculating it might house a secondary control center for the rear half of the body. German scientists Branca and Waldeyer escalated the claim dramatically, asserting that this sacral brain independently managed digestion, sex, and daily routine while the head brain handled higher functions. The idea lodged itself in popular culture immediately. Dinosaur comics, children's books, museum placards all repeated the 2-brain story for decades. It made intuitive sense. Stegosaurus was massive, lumbering, clearly not intelligent. Of course, it needed a second brain just to operate its back legs and tail. Modern paleontologists emphatically reject this. What Marsh found was a sacral plexus, a completely normal concentration of peripheral nerves branching off the spinal cord to innervate the massive hind limbs and tail. It lacked the layered, complex structure of a true brain and had zero capacity for conscious processing. Every large animal has enlarged nerve clusters at major limb junctions. The leading hypothesis now is that the space housed a glycogen body, an oval mass of carbohydrate-rich cells found in modern birds that may provide metabolic energy to the nervous system or aid in balance and coordination. As for the walnut-sized brain claim, that's exaggerated too. The actual endocast volume measured 64 milliliters, closer to a lime or a small dog's brain, weighing roughly 70 to 80 grams. The encephalization quotient, the ratio of brain size to body size, was about 0.2, which does place Stegosaurus near the bottom among dinosaurs. Humans score roughly 7 for comparison, but as Emily Buchholz demonstrated in 2012, this was perfectly consistent with the undemanding cognitive requirements of a slow-browsing herbivore. Stegosaurus didn't need to solve puzzles. It needed to eat plants and not die, and it succeeded spectacularly. Stegosaurus survived for millions of years, a far longer run than Homo sapiens has managed so far. Its bony plates, once thought purely defensive, likely served thermoregulation and display functions hinting at some degree of social behavior. The image of a stupid dinosaur so dumb it needed 2 brains to function is a myth built on outdated science and mockery. Stegosaurus was exactly as intelligent as it needed to be. But if 1 brain was enough for a giant armored herbivore, what about the claim that all dinosaurs were cold-blooded, sluggish reptiles? Cold-blooded dinosaurs? From the moment Richard Owen coined the term terrible lizard in 1842, dinosaurs were treated as oversized reptiles, sluggish, swamp-dwelling, cold-blooded creatures that sat in the sun waiting to warm up enough to move. This image dominated from the 1920s through the 1960s, an era paleontologist Robert Backer called the dinosaur doldrums, when dinosaurs were considered evolutionary dead ends so boring they barely warranted study. Museums displayed them as failures failures, textbooks framed them as inferior prototypes that mammals replaced. And everyone accepted it because they were reptiles, and reptiles are cold-blooded, except the evidence never supported this. The revolution began with John Ostrom's 1964 discovery of Deinonychus, an agile predator with hollow bones, a horizontal posture, and sickle claws that implied a metabolism far beyond any modern lizard. Ostrom's student Robert Bakker became the chief evangelist, publishing The Superiority of Dinosaurs in 1968 and popularizing the term dinosaur renaissance in 1975. Their argument was simple. Dinosaurs dominated terrestrial ecosystems for 165 million years. Cold-blooded animals can't do that. Modern evidence has grown increasingly sophisticated. A 2014 study by John Grady in Science analyzed growth rates across 381 species and found dinosaurs occupied a middle metabolic zone called mesothermy. They generated metabolic heat internally but didn't maintain constant body temperature like mammals. This explained how sauropods reached enormous sizes without overheating and how smaller theropods stayed active in cool climates. Robin Dawson's 2020 eggshell isotope study at Yale measured formation temperatures in eggs from 3 major dinosaur groups. All were significantly warmer than their surrounding environments. Troodon eggs formed at temperatures 10 degrees Celsius above ambient. Maiasaura, 15 degrees warmer. The conclusion was that warm-bloodedness was the ancestral condition for Dinosauria. The most dramatic finding came from Jasmina Veeman's 2022 Nature study, which measured molecular waste products from oxygen respiration preserved in fossil bones. Theropods and sauropods registered as fully warm-blooded with metabolic rates comparable to modern birds and mammals, but some ornithischians, Stegosaurus, and Triceratops appeared closer to ectothermic ranges. This suggests the ancestor of all dinosaurs was endothermic, and some lineages secondarily evolved slower metabolisms as an adaptation, the exact reverse of what was assumed for a century. The simplistic cold-blooded versus warm-blooded binary is dead. Dinosaurs exhibited a spectrum of metabolic strategies depending on size, environment, and ecological niche, but the old image of sluggish swamp dwellers that couldn't regulate their body temperature is definitively wrong. They were active, dynamic animals that conquered every terrestrial environment on the planet, and they did it with metabolisms more complex and varied than we gave them credit for. But even understanding their metabolism correctly doesn't prepare you for how they actually died. The asteroid extinction. The popular story is beautifully simple. Rock falls from sky, dinosaurs die, mammals inherit the Earth. The Alvarez team's 1980 discovery of anomalous iridium levels at the Cretaceous-Paleogene boundary, followed by identification of the 180-kilometer Chicxulub crater off Mexico's Yucatan Peninsula, gave the narrative a dramatic simplicity that media and textbooks loved. One bad day 66 million years ago. Lights out for the dinosaurs. Except that's not remotely what happened. The extinction was a multi-mechanism cascade spanning years to decades, and the asteroid was only the opening act. The immediate effects were apocalyptic but localized. A magnitude 10+ earthquake. Superheated plasma vaporizing everything within hundreds of miles. Mega tsunamis washing over coastlines. But those killed a fraction of life on Earth. The real killing mechanism was the impact winter. Dust, sulfur aerosols, and soot from global wildfires blocked sunlight, reducing solar transmission to 10 to 20% of normal for 8 to 13 years. Photosynthesis collapsed, food chains disintegrated from the bottom up. Temperatures dropped by up to 25 degrees Celsius. Acid rain acidified the oceans. Animals didn't die in an explosion. They starved and froze in the dark. But here's where it gets complicated. Earth was already stressed before the asteroid hit. The Deccan Traps eruptions in India, one of the largest volcanic events in planetary history, had begun roughly 250,000 years before the impact. Two landmark 2019 studies published in Science, one from Princeton and one from UC Berkeley, agreed the eruptions spanned approximately 1 million years, bracketing the impact perfectly. Trillions of tons of carbon dioxide and sulfur pumped into the atmosphere, destabilizing global climate for hundreds of thousands of years. A 2020 study by Chiarenza and colleagues in the Proceedings of the National Academy of Sciences ran climate models and found something surprising. surprising. The impact winter alone was sufficient to destroy dinosaur habitats globally, but the Deccan carbon dioxide warming may have actually buffered the cooling effects, paradoxically helping some species survive longer than they would have otherwise. The asteroid and the volcanoes weren't competing theories, they were compounding disasters. The extinction killed 75% of all species, every non-avian dinosaur, every pterosaur, every mosasaur, every ammonite. Analysis of fossilized fish from the Tanis site in North Dakota revealed the asteroid struck in spring based on bone growth patterns, meaning animals in the northern hemisphere were in breeding season. The impact hit a sulfur-rich gypsum seafloor that maximized atmospheric poisoning. If it had struck almost anywhere else on the planet, the extinction might have been far less severe. The dinosaurs didn't die in a day. They died over years of darkness, cold, starvation, and ecosystem collapse following a cosmic accident that hit at the worst possible time in the worst possible place. But here's the thing, they didn't actually go extinct. Birds are dinosaurs. This final myth might be the most profound because the common understanding that dinosaurs are gone is flatly incorrect. Birds are living theropod dinosaurs, and with over 11,000 species, they are the most diverse group of land vertebrates on Earth, outnumbering mammals roughly 2 to 1. By this measure, dinosaurs are more diverse now than at any point during the Mesozoic. Every pigeon on a windowsill, every chicken nugget, every hummingbird at a feeder is a dinosaur. And the evidence for this is so overwhelming that denying it requires ignoring entire fields of science. The evidence chain stretches back to 1868 when Thomas Henry Huxley noted striking similarities between Archaeopteryx, small theropods, and ostriches. His insight was derailed for 40 years by Gerhard Heilmann's influential 1926 book, which argued dinosaurs couldn't be bird ancestors because they apparently lacked clavicles, the collarbones that fuse into the wishbone in birds. This was factually wrong. Clavicles had already been found in Oviraptor, but weren't recognized as such. John Ostrom revived the hypothesis with Deinonychus in 1969, and Jacques Gauthier's rigorous 1986 cladistic analysis firmly placed birds within Theropoda as a subgroup, not descendants. The feathered dinosaur discoveries from China's Liaoning province beginning in 1996 provided overwhelming physical confirmation. Sinosauropteryx, Microraptor, Anchiornis, dozens of species showing the gradual transition from simple filaments to complex flight feathers. Molecular evidence sealed the case completely. A 2008 science study extracted collagen protein from a Tyrannosaurus rex bone and sequenced it. The molecular structure showed closer kinship to chickens and ostriches than to alligators or any living reptile. Birds descended from Saurischian, lizard-hipped dinosaurs, not ornithischian, bird-hipped dinosaurs. That naming irony has confused biology students for generations. And here's the beautiful part. Birds didn't descend from dinosaurs the way humans descended from apes. Birds are dinosaurs the same way bats are mammals. Evolutionary lineages don't stop being what they are just because they develop new characteristics. Feathers, flight, beaks, none of that disqualifies them from dinosauria. As for the persistent belief that humans and dinosaurs coexisted, held by a startling 40% of Americans in some polls, and fueled by the Flintstones and young Earth creationism, the gap is 63 million years. Non-avian dinosaurs vanished 66 million years ago. The genus Homo appeared roughly 2 to 3 million years ago. The only dinosaurs humans have ever encountered are birds. You've probably seen dozens today. Dinosaurs didn't go extinct. They evolved, survived the greatest catastrophe in planetary history, and became the most successful flying animals Earth has ever known. They're still here. And they're still dinosaurs. If you enjoyed this video and want to see more, click the video on the screen now.